Very good morning to one and all. I welcome you on the 12th day of this 2-week advanced online professional training program on utilization of nanomaterials and instrumental methods for energy applications. So far, we have received a detailed insight on the conceptual understanding of different categories of advanced nanomaterials, their synthesis, characterization, and applications. We also understood theoretical and practical aspect of instrumental techniques like XRD, different types of thermal analysis, electron microscopy, and so many others. From last 3 days, we are focusing on different electrochemical energy storage and conversion technologies and continuing in the same direction. Today we have sessions on hydrogen storage technology, which has recently received a lot of attention of the scientists all around the world. So our technical speaker of the day is Professor Pratibha Sharma from IIT Mumbai. Her first morning session would be on hydrogen production routes from hydrocarbons and renewables. And the second session, the noon session, will be on storage, transportation, and safety aspects of hydrogen as energy carrier. So first of all, let me introduce our speaker to the audience. Professor Pratibha Sharma is currently working as Professor, Department of Energy Science and Engineering, Indian Institute of Technology, Bombay. Her research interests include hydrogen storage materials and systems, hydrogen utilization, low-cost earth-abundant materials for photovoltaic applications, and materials for biomedical applications. She has worked on various types of hydrides for solid-state hydrogen storage, their modifications, catalysis, support, and tailoring the reaction mechanisms. She has been working on simulation, design, and development of hydrogen storage reactors for various applications. She is currently on the editorial board of international journals, reviewer for several renowned international journals, serving on the organizing and advisory committees of a large number of conferences. She has delivered several invited talks and keynote addresses in different international conferences. She has supervised 16 PhD students, more than 40 MTech and MSc students, and more than 90 referred international journal publications, and 4 patents are there to her credit. She has been awarded with the Outstanding Service Award by the International Association of Hydrogen Energy for her phenomenal contribution towards the world hydrogen economy. Professor Sharma is leading several multi-institutional R&D projects on hydrogen system development and integration for different applications. These projects have several IITs and industries as partners, which are working together for hydrogen-based solutions. She has established a multi-institutional R&D center on hydrogen at IIT Bombay with DST funding. She has international collaborations with several countries, and to name a few, they are Canada, Japan, Australia, England, France, South Korea. Madam, on the behalf of Suresh Gyan Vihar University, Jaipur, I extend hearty welcome to you. And now I request you to start the session. So I hand over the session to you, ma'am.
Thank you, Dr. Kriti. Am I audible?
Yes, ma'am, you're audible.
And thank you, Dr. Ankur Jain, for giving me this opportunity. I will share my screen. So is this visible and in full screen?
Ma'am, it is visible and it is also in the full screen.
Okay, thank you. Thanks for the introduction. This first talk, I will be focusing on the different production methods from both hydrocarbons as well as renewables. As Dr. Kriti rightly mentioned, that there has been a hype about the hydrogen and its interest is renowned. Like it is from the industrial sectors, from the various stakeholders, from the policymakers side, government, even from the consumer end, there is a lot of interest which we have seen in the hydrogen. And this is nothing new as well for hydrogen. It has seen several such waves of interest in past as well. Like in 1970s, this interest was basically derived because of the oil price shocks. Then 1990s, early 2000, that was again because of the concerns which came because of the global climate change issues. And then we can again see this hype from 2018 onwards. But then we can say that this difference is, compared to the other waves, this interest will persist. The reason being, earlier what we have focused was application of hydrogen only for vehicular application, and the entire government fundings, whether it was the stakeholders' interest, was basically diverted towards FCVs. But the difference now is that we have identified that there are wide range of possibilities with hydrogen, and that interest is also in various sectors and segments. So that seems that this is an ideal time where the technologies can be scaled up, economies of scale can work well, and then we can have learning by doing. So as the economies of scale is there, and then we see how the scaling up gives us more knowledge to further improve the performance, efficiency of the hydrogen technologies. Now, if we quickly see some of the major initiatives that are there, there are several roadmaps, strategy documents, mission documents, which various countries are coming up with. And we know many of these, like the Germany's first fuel cell train. This is known, was in news, and now they are coming up with few more trains. China, they have a target of 1 million FCEVs by 2030 and 1,000 hydrogen refueling stations. They are planning to have a hydrogen energy park area with an area of 130,000 square meter. Japan, they have launched their hydrogen mobility program. So similarly, there are several countries, including India, who are coming up with their strategic documents. Now, these strategic documents, they have certain targets which are defined, and there are certain targets which are considering that by 2050 or by 2060, depending upon which country has announced which year they want to go to net zero target. So all these are increasing that interest. Now there are different countries which have their hydrogen missions, like to name a few: Japan, China, US, Australia, Germany, France. They have all come up with a strategic document. There are automotive industry, OEMs, various OEMs which have come up with various prototypes, designs, various vehicles into the market. There are different councils which are formed where companies are partnering and they are bringing in funds. So there is an investor interest as well, which is coming up globally. So if we see globally, then there are incentives which are given so as to meet out these targets. There are targets which have been launched without incentives. And then there are both. As well as there are incentives which are without targets. Depending upon what is the advancement scale of a hydrogen technology, these have been defined. Now, let us first understand why this interest is coming globally for use of hydrogen. So some very simple things that we all know, I will just reiterate those, that it is hydrogen, since it is very abundant as against the other fuels, which we know that at one point of the time it will deplete. But hydrogen, since it can be produced from a wide variety of fuel, wide variety of sources, so it may sustain over a longer period of time. That we know that. At the same time, it has very high energy density. At the point of usage, it is clean and green. It even offers to decarbonize a wide variety of sectors. including the industrial sector, the transport sector, the polluting sectors like the chemical, iron and steel, they are also opting for hydrogen, including a certain percentage of hydrogen in their usage so that they can reduce their carbon dioxide emissions. Hydrogen, it is a versatile fuel. It's a versatile energy carrier because we can use any of the source of energy to produce hydrogen. And that can help us with energy security. Because currently we know that in the current scenario itself, we can see the worries because of the crude oil increase in the prices of the crude oil because of the Russia-Ukraine war. So since we are dependent heavily on imports, if we have ways of producing hydrogen through different routes, we can have a better energy security in terms of we will be self-sustainable in that case. At the same time, the systems which are using hydrogen, the energy conversion devices, they have more efficiency, they are more reliable. So the entire electricity generation process can be more efficient when we use hydrogen. Now then it comes to why the industries will switch until and unless there is a penalty of carbon dioxide pricing. But we have to understand that hydrogen can easily fit into their infrastructure. Maybe not much of modifications would be required. And industries have already been using, the major industries have been using hydrogen since decades. The difference will be that hydrogen could be introduced in a cleaner and greener manner to decarbonize those sectors. So we have been using hydrogen in sectors like chemical industries and refineries from mid of 20th century or even earlier. So the transition will not be very abrupt. We will be using those technologies. We have a knowledge of using hydrogen in those areas. So it won't be abrupt that suddenly we have turned off the fossil fuels and we have started hydrogen. At the same time, it can offer help for various renewables in the form of providing long-term large-scale storage. So these are some of the benefits associated with hydrogen. I have listed down some of those here. And then when we use hydrogen, there are several advantages. When it comes to, say, transportation sector, we can drive longer with use of hydrogen compared to the battery electric vehicles. Filling could be faster. When it is used for different processes, whether it is combustion, when we burn it, it is clean and green. We can scale it up easier. It is easier to scale up compared to even battery system. And when it is used, we can decarbonize several industrial sectors. There are a wide number of applications where hydrogen can be used. It can be used for power generation, for domestic applications, for various industrial applications, vehicular application, navigation, and space applications. Many of these we have already been using it. Now let us come to the topic which I will be discussing in this talk. So the status of hydrogen production globally, if we see, it's about 90 million tons of hydrogen which is being produced globally. And out of that 90 million tons, about 79% of it, 72 million tons, it is produced in dedicated hydrogen production plants. What do I mean by dedicated hydrogen production plants? That it is meant to produce hydrogen and that is its primary product. The remaining, which is 18%, 18 million tons, 21%, that is where hydrogen is obtained as a byproduct. Like an example of byproduct is in the chloralkali industry, where when the caustic soda, when the electrolysis is done to produce NaCl, the hydrogen is obtained as a byproduct. So out of that 90 million tons, if we see from which fuel hydrogen is being produced, the dominating fuel, the major fuel which is used to produce hydrogen is natural gas. And natural gas, we know that its major constituent is methane. There can be other components like ethane, propane, butane. Then there can be H2S, carbon dioxide, nitrogen. So there can be other constituents as well. But 59% of the hydrogen production today globally is by means of natural gas as a fuel. 19% using coal, 0.6% using oil in refineries especially, and 0.4% is used or obtained from low carbon technology. By low carbon technology, we mean electrolysis, where it is dedicated electrolysis. Hydrogen is the major product, and it is 0.03% wherein electrolysis is used for hydrogen production. And the remaining is fossil fuel plants, but they are integrated with carbon capture, use, and sequestration. And 21% of it comes as a byproduct hydrogen. So this is an overall breakup. So if we see, this also includes the fossil fuel based production. So if we quickly look at these numbers, we can see that majority of hydrogen is still being produced from fossil fuel. And there are reasons for it that we will see. So this is global status. In India, we have an annual production of 6 million metric tons. And out of this, 3.2 demand is in refineries, 2.6 million metric tons per annum is in fertilizer industry, 0.2 million metric tons per annum is in chlor-alkali industry, and this is the byproduct. So overall 6 million tons of hydrogen is being produced. Now, just now we have seen that it can be produced from different fuels. Now, based on from which fuel it is being produced, there is a color coding which is assigned. Hydrogen itself has no color. It is colorless, odorless, tasteless gas. Just to identify from which feedstock hydrogen is being produced, and color has been assigned. So if it is being produced from bituminous coal, then it is black. If it is being produced from lignite, then it is brown without CCUS. If it is being produced from natural gas, it is gray. If produced from renewables, then it is green. If produced from fossil fuels, but carbon capture, use, and sequestration has been integrated, then it is a blue hydrogen. A new color is turquoise, which is when hydrogen is being produced from methane pyrolysis. Now there are several other colors which are coming up, whether it is being produced from biomass or from nuclear, but they have still not been finalized. So an entire spectrum of this color will soon come up. So we will quickly see what are these methods, what are the ways in which we can produce from these feedstocks. Now, as I mentioned that the 90 million tons of hydrogen produced globally, out of this 72 million tons is pure hydrogen and 18 million tons is mixed hydrogen. Now 72 million tons, this is used as a pure hydrogen. It is for fertilizer industry and refineries. And another 18 million tons, this is used for methanol production, for DRI, direct reduction of iron in the steel industry. So this is about the demand. Now, why we are using fossil fuels for hydrogen production? There are very clear-cut reasons for it. Although when we say that hydrogen is a green energy carrier, we need to understand that what we are doing is, if we are producing from fossil fuels, we are still emitting the emissions, and only at the utilization point it is clean and green. But although the scenario is changing, now the focus is shifting towards green hydrogen, wherein we are using renewables for production. So there will be a short term wherein we will still depend upon fossil fuel, intermediate term when both fossil fuel as well as cleaner hydrogen, greener hydrogen production from renewables will take up. And finally, what is expected in long term, it will be from renewables only, or with fossil fuels with CCUS, so that the entire hydrogen value chain becomes clean and green. Now let us see that why hydrogen is basically produced from hydrocarbons. Reason is these are at present available, easily available at our doorstep. These are cost competitive. So the hydrogen which will be produced from fossil fuels is very competitive. It is easier to use them. It is convenience in the storage and distribution. At the same time, they have a high hydrogen to carbon ratio. So when we see a fuel, what do we look at is that it should be inexhaustible, it should be clean, convenient, and independent from the foreign control. So hydrogen can thus play a key role in all these. But when we decide that which method we are going to use for producing hydrogen, there are a number of key points that are looked before deciding into which method of hydrogen production will be used. The first and foremost is feedstock. What is available? Feedstock means what is the raw material, the starting material for hydrogen production, whether it is available. For example, if it is India, then we have ample amount of coal. Although the problem is, we all know it is a high ash content coal. But if a particular country has a certain feedstock which is available in abundance, they will prefer to use that feedstock for hydrogen production as against depending upon imports. So feedstock availability, and definitely if it is available, then the cost will be lower compared to what you get from imports, is the key point while deciding which hydrogen production route will be used. Secondly, in what capacity you want to generate hydrogen, in what capacity you want to produce hydrogen. It can be very low, few normal meter cube per hour to lakhs of normal meter cube per hour capacity. It could be tons to thousands of tons of hydrogen being produced per hour. So that capacity, like that will differ from whether it is a centralized plant or a decentralized plant. That also determines what will be the hydrogen production method. Just to give an example, if I want this hydrogen being produced on a tabletop in a lab scale, then I will go for an electrolyzer. But if my requirement is for an industrial scale, a chemical production plant, an ammonia synthesis facility, then economies of scale for producing hydrogen will work very well for steam methane reforming. So depending on what is your capacity requirement of the utility, the production route can be different. Then it comes on to the product purity. If it is to be used for fuel cell, it has to be highly pure, ppm level pure. So I will go for electrolysis. However, if the purity requirements are lower when it is to be used in IC engines, I may not worry about whether it is from electrolyzer, which adds up to the cost. So I will not go for, but I can use any other method producing from hydrocarbons. Then what is the pressure requirement? That we will see what is the advantage of having hydrogen production plant operating at a higher pressure, because we can save in terms of the compression power. And what are the side products which we are getting other than hydrogen? Sometimes those products have a value added to it, and that also makes the process cost effective. And finally, whether we need cogeneration of steam and power. Just to quickly again see what could be the reason why we are using fossil fuels. So this is the theoretical energy consumption in producing hydrogen from different feedstocks. If it is natural gas or LPG, naphtha, heavy oil, coal, and water. So we can see that by electrolysis, the requirement of energy is several times higher as compared to hydrogen, the energy required in producing hydrogen from fossil fuels. At the same time, the hydrogen yield which we are going to get when it is being produced from natural gas as against the other hydrocarbons is much higher. And that is the reason globally why 60%, close to 60% of it is being produced from methane or natural gas. So we can produce this from fossil fuels, natural gas, gasoline, naphtha, coal, heavier fractions. We can even produce hydrogen from renewables. It can be wind, solar, biomass, nuclear. Now, starting from with the hydrogen production from various hydrocarbons, we can categorize the methods of hydrogen production from different hydrocarbons depending upon whether it is an endothermic, the thermodynamic viewpoint. It can be an endothermic reaction, exothermic reaction, basis of the catalyst, whether it is catalytic reaction or non-catalytic reaction. whether it is an oxidative, so we are using an oxidant in it or not, then it can be oxidative or non-oxidative. However, the major way of characterization of the different technologies for hydrogen production is based on the oxidant. Again, there are large number of ways of producing hydrogen. Oxidative can be further categorized into steam methane reforming, autothermal reforming, partial oxidation, and we can combine two of these methods to get a combined reforming, steam iron process, carbon dioxide reforming, plasma reforming, and similarly non-oxidative routes wherein we don't use oxidant. And these can be further classified. We will not be going into the details of it since this is a 1 hour talk. All this like production we used to cover in a classroom course in 20 or more hours. So what is the difference between an oxidative process and a non-oxidative process? The name itself tells there is an oxidant present, then it is an oxidative process, and that oxidant reacts with the hydrocarbon to produce syngas. What is syngas? Synthetic gas, which is a mixture of carbon monoxide and hydrogen. Depending upon what is the hydrocarbon being used, we will get that ratio of hydrogen to carbon monoxide in the syngas. So when an oxidant is used, this oxidant reacts with the hydrocarbon to give syngas. This oxidant can be either oxygen. If it is oxygen, then it is an exothermic reaction, so it is an oxidation process. If it is steam used, in that case, it is reforming process. Or if it is carbon dioxide, which is used as an oxidant, then it is known as dry reforming. So we can have either of these oxidants or a mixture of those. For example, if it is oxygen, then it is an exothermic reaction. If it is steam, it is an endothermic reaction. If it is carbon dioxide, it is again an endothermic reaction, or it can be a mixture like oxygen and steam, then it is a thermoneutral process. It can be oxygen and carbon dioxide. It can be three of these, so bi-reforming or tri-reforming. But the problem is that since the hydrocarbon which we are using, it is an inert, and if we are using steam, it is also an inert compound, operational temperatures required are higher. In order to bring down those operational temperature to a lower temperature, we have to use a catalyst. So catalyst plays a dominant role here. In the other category of conversion or production of hydrogen, this is a non-oxidative process where the hydrocarbons, they are converted into hydrogen and energy is supplied for producing hydrogen. Now, because there is no oxidant here, you have to break down this compound to get syngas or hydrogen and lower hydrocarbons. And that energy can be supplied. The energy required for breaking up of hydrocarbons to get hydrogen can be supplied either through a thermal electrical route or by means of radiation. And this is endothermic process only. So we will be looking at the oxidative processes first. The first and foremost method, as I mentioned, 59% is being produced from natural gas, and that process which is used for producing hydrogen is known as steam reforming. So it has certain steps. I will try to skip the chemistry which is involved in this. I will try to concentrate on what is the role of materials in each of these processes, because this is a conference which is a workshop related to the materials. So just trying to give you a feel of that the steps involved in a steam reforming process is, the first and foremost step is you are preparing the raw material for it to participate in the reaction. And that is known as feed pre-treatment. So you are making ready the feedstock, which can be methane. So the term is general, steam reforming. Now, if you are using methane, then it is steam methane reforming. If you are using ethane or alcohols or higher hydrocarbons, then it becomes steam reforming according to the feedstock used. Now, in this, the material is prepared, then it undergoes steam reforming process. This is the second step. Thereafter, it undergoes gas shift reaction, where we can still recover more hydrogen, and finally a purification step. Sorry, just a minute. Please don't call, I have a talk mode. So what happens in the feed pretreatment is we remove all the impurities. Now, why do we want to remove all the impurities? Because the major component of a steam reformer is we have several catalysts used, and these catalysts, in presence of hydrocarbons, a carbon layer is formed on them, and that's why they get deactivated. And these impurities which are present in the feedstock, they poison the catalyst. So we have to remove both the higher hydrocarbons as well as we have to remove all the impurities. Now these impurities can be sulfur containing impurities, these can be chlorine containing impurities. So there are different processes which are used for removing these impurities so that your feedstock gets ready. And usually in steam reforming process, whenever there is a higher hydrocarbon, it is converted into a lower hydrocarbon for the reforming process. Like if it is ethane, propane, butane, they are converted into methane. And finally, the reaction is steam methane reforming. So this is the overall process. These are the steps which are involved. So first step is desulfurization unit. Then it has to undergo a steam methane reforming. The two steps, it can be two-step process where we can recover more hydrogen, that is high temperature water gas shift or a low temperature water gas shift, carbon dioxide absorption, methanation. So depending upon what is the final purification step, the technological variations could be there. I will not go into the details of the reaction, just to show how the reformer tubes look like. Actually, a plant is much bigger than this plant. So the reforming reaction occurs in several tubes. These are the tubes in the reformer bundle. These tubes are externally heated using different burners, and these are filled with catalyst. So here catalyst, its support and promoter, they play a key role. Now these tubes, just to give you a feel of what is the size of the reformer, these tubes, they have about 7.5 to 12.5 centimeter inner diameter, 2 centimeter thick, and the height of the tubes can be between 12 to 15 meters. And there are hundreds of such tubes which are there in a reformer, which are filled with the catalyst. So once the feedstock is cleaned from the impurities, the natural gas along with steam is passed in these filled tubes, catalyst filled tubes, where the reforming reaction occurs. The temperature, exit temperature is very high. For the remaining reaction, the temperature needs to be lower. That heat is taken out to produce steam. Once it is cleaned using a pressure swing adsorption, the remaining gas also have a calorific value that can be used for burning in the burner. So the natural gas here can act as both. It can be a feedstock for producing hydrogen. It can act as a fuel for burning in the burner to provide the required energy. Now the major challenge in a reformer is the carbon which is formed through several steps. So these are not the only steps. Depending upon what is the feedstock, whether it is a higher hydrocarbon, there can be several competing reactions that can occur in a reforming plant. Carbon can get deposited and we have to get rid of it. So the proper design of catalyst, support and promoter is very important. Usually the catalyst, since large quantities of catalyst is used, it is nickel on alumina. Now when it comes to designing a reformer, it is not only the reformer heat transfer, but this entire system of catalyst, support and promoter plays a key role. And then gas needs to be cleaned. So it has to undergo several cleaning steps in the final process so as to get very high purity hydrogen. Like we can even get 99.999% purity when we use a pressure swing adsorption. And there are several steps in the pressure swing adsorption, and there are different material layers. So again, material here again plays a dominating role. So different layers of absorbents are used in a pressure swing adsorption, which sequentially removed impurities from the hydrogen flow stream. So this is the major method which is used globally for hydrogen production. Now the major problem that lies, if we see from the thermodynamic viewpoint, is this reaction, which is the steam methane reforming reaction. There are 2 moles combining to form 4 moles. So there is a volume expansion, volume increase. So what is required is that the pressure should be lower. But for any application, industrial application, the desired output pressure from a reforming unit is higher. So how can we take care of it? We can take care of it by sequentially removing any of the product. So this is hydrogen, sorry for this mistake. So this hydrogen can be removed, or the carbon dioxide which is formed can be removed. So there are advanced technologies which can be removed, wherein carbon dioxide which is formed can directly react with certain sorbents to produce a different product which can be regenerated back. So here the materials which play a dominating role are the sorbents, which are used for carbon dioxide absorption. There can be another way of looking at this problem of pressure increase, required pressure which is higher, and that can be membrane based separation, wherein we can use certain membranes to remove hydrogen selectively. And as such, the chemical equilibrium limitations will not be there. So we can have the catalytic bed where the reforming reaction will take place, producing hydrogen, carbon monoxide, and carbon dioxide. But then we have a membrane which will only allow hydrogen to flow through it. So we can have multiple processes taking place in a single reactor. And that is the advancement to steam methane reforming. Now, when we use steam methane reforming, definitely there are a lot of emissions involved. So about 900 million metric tons of carbon dioxide is released into environment because of the hydrogen production processes. And it's like roughly around 10 tons of carbon dioxide per ton of hydrogen, which is being produced using natural gas. So what can be done is to reduce the emissions. We can collect the carbon dioxide which is produced, not only from the off gas. What do we mean by off gas? Once you are separating hydrogen, whatever is left out is known as an off gas or tail gas. That when it is used as a fuel in the burner, the carbon dioxide which is released is a diluted form. If we capture from there, and if we capture the emissions related to the formation of hydrogen, we can capture 90% of the carbon dioxide, and that could be a sustainable method of hydrogen production, but that adds up to the cost. Now, another method could be a simple one: oxidize the fuel and then produce hydrogen and carbon monoxide. That is the syngas. Again, it can be catalytic and non-catalytic. Usually non-catalytic is used. The reason for partial oxidation of hydrocarbons is in refineries, which were actually earlier considered as a major producer of hydrogen, now they have become major consumers of hydrogen because they use hydrogen for various downstream processes, whether it is catalytic cracking, whether hydrogenation, hydrogen desulfurization, denitrogenation. And at the same time, what they do is they have a heavier, dirtier feedstock, which has a lot of impurities, which has heavy metals in it, heavier hydrocarbons. So they can upgrade the fuel using partial oxidation and can produce hydrogen. So the bottom of the barrel, which is the fuel which as such will go waste, that can be used when it is partial oxidation. Now again, the challenge remains is, since the reaction takes place at very high temperatures, so even the burner temperature can go to 3000 degrees centigrade. So the material constraints are there. So again, the materials design and the burner design plays a key role. We will not go into the chemistry of the reaction. So here in partial oxidation, this is a method which accounts for upgradation of fuel in refineries. The fuel which they cannot use, neither they can throw because it has certain calorific value, they can upgrade this using partial oxidation. A mix of the two process, reforming and partial oxidation, which takes into advantage of each of the two methods, is autothermal reforming, where we are using both the oxidants, oxygen and steam. And that has advantage that the required energy for reaction is not provided by an external source by heating the tubes of the burner in the reformer, but we can still get a higher hydrogen concentration, unlike which was in partial oxidation. So both the advantages is taken into consideration using an autothermal reformer. Again, materials plays a dominating role. What will be the tube metallurgy? What will be the metallurgy of the reactor? What will be the design of the burner? What will it be made up of? All that decides onto what will be the efficiency of the process. Hydrogen can also be produced using coal gasification. Coal, we have seen, it is a major process producing 19% of hydrogen globally. And it is a very simple step. We will not go into the chemistry. It is a very simple step that can take place. It is a water splitting reaction, wherein you have a M species M, which fix the oxygen which is present in water, and hydrogen is being produced. So this is a reduction oxidation reaction. Now this M can be carbon in the coal. It can be some other metal. So metal oxide based reduction oxidation reaction. Now when such a reaction occurs, it can be in the presence of oxygen, it can be in the presence of steam, it can be pyrolysis, it can be gasification, it can be oxy-steam gasification. So there are different routes of it. But since the carbon content is higher compared to the hydrogen content in coal, the H2 by CO ratio, the hydrogen to carbon monoxide ratio in the product gas is much lower compared to the methods we have previously seen. Just to give a brief overview of what is the current status. Globally, about 130 coal gasification plants are in operation, and majority of it are in China. And they have about 80 coal gasifiers that produce 8 million tons of hydrogen per year. And that is roughly equivalent to the 12% of the global dedicated hydrogen production. It results in a lot of emissions, so we should always have carbon capture, use and sequestration ideally, but that adds up to the cost. Hydrogen can be produced from renewables as well. It can be produced from biomass. The route could be either biochemical or thermochemical. If it is biochemical, then it could be digestion or fermentation that could produce biogas, acid, alcohols, and different gases. If it is thermochemical, then it can be gasification producing syngas. And then syngas can be purified to get hydrogen and carbon monoxide, carbon dioxide separated. But the biggest challenge in biomass-based production is the formation of tars. Hydrogen can be produced, as I mentioned during the color code, that a new method, it's not new in fact, this was used in 1960s as well, and this was known as carbon black method. This was used for producing carbon at that time, and hydrogen was a byproduct at that time, but now that interest has come back. There are several reasons, because when you break down a hydrocarbon, you are getting solid carbon and hydrogen. So it is very easy to separate. Separating hydrogen from carbon monoxide and carbon dioxide, all three being gases, is difficult compared to separating it from a solid product, which is because of the density difference, phase difference, it can be easily separated. At the same time, since carbon dioxide, carbon monoxide is not formed, so the emissions will be less. Other than that, the carbon which is obtained, depending upon the conditions, it can be exotic form of carbon, nanotubes and all, which can be used for various energy storage applications. So as such, both the products have their use, whether it is carbon or hydrogen in this process. And there are several plants which are coming up based on methane decomposition. Now, towards renewables, if we see, it can be produced from electrolysis. Roughly about 0.3% of hydrogen is currently globally being produced from electrolysis. And a majority and certain part of it is coming from as a byproduct in a chloralkali industry. Now, the problem that people used to foresee is where from this water will come. So there are plants which are coming up where seawater can be used through desalination route, but that will be adding a very nominal cost to the hydrogen. So that is another way of utilizing the water for electrolysis. Now, if we quickly see, all of you know that the electrolysis process is that water, when you are giving certain amount of energy, it can break down into its constituents, hydrogen and oxygen. And this energy, if it comes from electrical energy input, then it is electrolysis. If it comes from heating, thermal energy route, then it is thermolysis, but the temperature required are above 4000 K because it is a non-spontaneous process. or it can come from combined. It can come from chemical as well as thermal route. Then those are known as thermochemical processes. So we will quickly look at the electrolysis route. When we talk about an electrolytic cell, which is the basic unit of an electrolyzer is the device which is used for doing electrolysis of water to produce hydrogen and oxygen, but that has a stack of different electrolytic cells. A basic electrolytic cell has few components. There are two electrodes which are used. There is a separator or diaphragm, and then electrolyte. Now, depending upon which electrolyte is being used, the technologies are different. If it is an aqueous solution of KOH, then it is alkaline electrolysis. If it is an acidic electrolysis with a membrane as a separator, then it is polymer electrolyte membrane. If it is a membrane having or a diaphragm having oxide conduction, O2 minus ion conducting through it, then it is solid oxide electrolysis. And now there is a recent technology which is coming up, which is anion exchange membrane, which allows a membrane which allows OH minus ions to flow through it. So depending on what electrolyte we are using, the technology could be different. So roughly we require actually 1.23 electron volt theoretically if water is being present in the vapor form. However, if it is present in liquid form, we may require 1.48 volt. But in actual conditions, the electrolysis occurs when the voltage to be delivered is 1.8 to 2.06 volt. There are certain extra voltages which are required for electrolysis, and they arises because of the various losses and irreversibilities present in the system as against the theoretical system. So we can have an alkaline electrolyte, which could be KOH, and this diaphragm which allows selectively OH minus ions to flow through it. So on the cathode side, the water takes up 2 electrons to produce hydrogen and OH minus ions. OH minus ions move across the diaphragm onto the anode side, undergoing recombination to produce oxygen. So oxygen evolution is always at the anode side. Hydrogen evolution occurs at the cathode side. 2 electrons which are liberated can pass through the external circuit. This is a very basic reaction for an alkaline electrolyzer. But the problem associated with alkaline electrolyzer is we are using a porous diaphragm. So there is a limitation to the current density. There can be intermixing of the gases at a higher current density, and they usually are very respondent, or their response towards any load variation or current variation is relatively slower. So the other method could be where these disadvantages are taken into consideration is the polymer exchange membrane electrolysis or proton exchange membrane electrolysis or polymer electrolyte membrane electrolysis, where you use a membrane instead of a diaphragm or separator. And that membrane allows H plus ions to flow through it. So similar reactions will occur. Again, the major challenges when it comes to electrolysis are the electrocatalyst, because in case of proton exchange membrane electrolysis, we are using an acidic electrolyte. So the corrosion is a major problem. As such, we will have to use expensive metals, which are the noble metals which are used, and that adds up to the cost. Membrane, which is the Nafion membrane, that is expensive. So the challenge in terms of materials when it comes to electrolysis is the availability of membrane and electrocatalyst, and that can reduce the cost. Now, not only these components, there are several other components like the gas diffusion layers, bipolar plates. So all those are the integral part of a proton exchange membrane electrolysis. A high temperature electrolysis can also occur where steam is used instead of water, and the required energy, so the total energy which is required for electrolysis, partly it can be thermal energy and partly it can be electrical energy. If the thermal energy input is higher, then the required electrical energy input is comparatively lower, and that happens in solid oxide electrolysis. So it takes place at a higher temperature. That high temperature can come from either waste heat, or it can come from a nuclear power plant, it can come from a solar thermal plant. But the problem here lies is the oxide conduction. Since the temperature is higher, so the materials challenges, degradation of the material occurs. We want better materials so as to have a better efficiency and life. We can compare each of these technologies. Like one technology has an advantage that it has a lower cost. Other technology, PEM, has higher current densities. It has better, these are more compact but expensive. SOEC, requirement of electrical energy, is less, so energy efficient, but then still there are degradations associated. Till 2000s, we were talking about electrolyzer projects where the size of the project used to be 0.1 megawatt. Now by 2010, we have started talking about projects of 1 megawatt. And currently, the projects which are coming up globally, they are in the size of hundreds of megawatt, a gigawatt as well. And there are various leading manufacturers, which are now coming up for the manufacturing of electrolyzer. Now, these electrolyzers can be combined with any of the systems like solar photovoltaic or wind energy system to produce hydrogen, and then the complete value chain of hydrogen will become clean and green. So if we compare, then still the cost of producing hydrogen is lowest when it is to be produced from fossil fuels. And that's why majority of the production is currently from fossil fuels. Production from renewables as well as from electrolysis process using renewable power to electrolysis is still the most cost-intensive method. But however, the scenario will change. That is the projection. In the net zero scenario as well as in the long term, what is expected is that with the increased renewables deployment, the renewable power price will come down, which is substantially lower in India compared to the developed world. The price of power, which in fact in electrolysis or renewables-based hydrogen production, renewable power accounts for 50% to 90% of the cost of that electricity. Now, once that power cost comes down, renewable power comes down, cost comes down, the deployment of renewables increases, electrolyzer capacities increases, the economies of scale works well. And then once we have scaled up these plants, we have a knowledge of operating such plants to improve their efficiency, to reduce the cost of materials being used. All that will in future bring down the cost of production of hydrogen from various renewables. So that is what is the forecast in the various country pledges which is coming up, whether it is the net zero policies which are coming up in the different countries or globally. To quickly see a sort of cost comparison in the Indian perspective, if we see the cost when it is being produced from steam reforming, it is 150 rupees per kg. When from coal gasification, current price is 245 rupees per kg. Biomass gasification 258. Microbial hydrogen production using from biomass, it is 813. When it is being produced from electrolyzer and alkaline water electrolysis route, then it is 433 rupees per kg. Now we need to also understand that, Ankur, how much time I have?
Ma'am, actually we have 5 minutes left, but you can extend for a few minutes if it is required.
Okay, no, I will quickly summarize and then we can take up questions.
Sure.
So we have to understand that this is the only route which is producing pure hydrogen, and pure hydrogen to the grade of 99.999%. That is electrolysis. But rest of the method, even the biomass gasification, we also get the other impurities or contaminants, and that are like depending upon what is the initial feedstock used, raw material used, and the production technology, because you are using oxidant. An oxidant will react to produce the various carbon emissions, CO, CO2. That separation and purification of hydrogen from it to get pure hydrogen, that also adds up to the cost. So even at times 40 to 50% cost of hydrogen comes from the separation and purification, capex and opex, capital expenditure and operating expenditure. Including that, like if we just try to get a feel of, if we have hydrogen at 99.9% purity, then the cost may be $11 to $12 per kg. If it goes one more 9%, then the cost that increases is tremendous. So that purification and separation cost is, that also adds up. The fuel cost adds up. If it is from renewables, then the electricity price, that adds up. So there are several components associated with it. Now we have to also see that this is not the cost of producing hydrogen. When the customer is buying at the refueling station, the cost is of entire value chain. It is from production, then purification, then you have to compress it to the required pressures so as to take it from one place to another. That involves bottling and transport as well, and delivery, final delivery at the site of its usage. So all that cost also adds up to the final hydrogen cost. Okay, so thanks. So I gave a very brief overview because as such, there is much more, many more things to be discussed in each of these technologies that I have just touched upon. Thank you.
Thank you so much, ma'am. It was really a detailed information for us on different methodologies for hydrogen production. So now let me take the questions we have received from the participants. The first question I have is it environmentally sustainable process to generate hydrogen from fossil fuels?
Yeah, so it is not. So it is not a sustainable method. But why we are doing it? Because this is cost effective. So producing, as I have in my earlier slides, I have told that this is the lowest cost option. So the strategy which is there is, in short term, it will continue, but it is not a sustainable method. In intermediate term, it is expected there are two scenarios. One is the announced pledged scenario, where the countries, they have made several announcements in terms of targets, in terms of the numbers that they have come up. It is predicted that by 2030, although the time seems very near, 70% of it will be produced from either renewable route or fossil fuel plants with CCUS. And 2050, it will be completely without emission. So the entire value chain will be zero emission. And that is the net zero scenario. So definitely it is currently not sustainable, but in long term, that is what the efforts are going on globally to make it sustainable.
Thank you so much, ma'am. Next question is how hydrogen is separated from its byproducts of any production process. What are the factors affecting percentage purity of hydrogen?
Yes. So I will give a very brief answer because this again may take a lot of time. There are 4 methods for separating hydrogen from its other constituents. The first and foremost is absorption-based method, which I have shown a diagram, but I didn't have time to explain. That is pressure swing adsorption, where you adsorb all the impurities leaving behind hydrogen. So what you get is the pure product, hydrogen. Second method is absorption-based method, where the major product, carbon dioxide, is absorbed, not absorbed, it is absorbed. And what is left out is hydrogen. The third method is membrane-based separation, where membranes are used which either allow impurities, those are carbon-based membranes, or most of the membranes just selectively allow only hydrogen to flow through it, so we can separate it. And finally, there is a cryogenic distillation or cryogenic method, where each of the components can be obtained separately. So these are the 4 methods which are used. And purity, definitely. If you use carbon dioxide absorption based method, you can get 95 to 97% purity. But if the product has a higher composition of carbon dioxide, you use that first and then couple it with a smaller pressure swing adsorption so that you can get a higher purity. So hybrid systems can be used to attain a higher purity.
Thank you so much, ma'am. The next question is, what are the limitations of electrolysis process of hydrogen production?
Okay, so some of the major limitations I have told. Currently, the cost of electrolyzers is very high. So this is roughly about, range is 1,000 to 1,500 per kilowatt is the cost. Although there are instances where reported where even in China, so which is again a leader in making electrolyzers, Europe, China, Canada, US, there they have reported even the price as low as $500 per kilowatt. But again, then there are certain questions to be answered. Price is the major limitation. Why prices are higher? Because we are using expensive materials, both membrane as well as electrocatalyst. Then there are other limitations, which are technology related limitations. Like alkaline, you cannot use for higher current densities. You cannot get very high pressures. That is associated with the technology. What are the materials we are using? PEM, the price is higher. And then acidic electrolysis, so you have to use high costly materials. PEM is better when it has to match with the renewable power, because the variations with the load or electricity, it very fastly replicates. So PEM is better in that sense. SOEC, high temperature, so the degradation is more. AEM, the anion exchange membrane, the process is slower, the materials are not stable. So these are, so every technology, it has other limitations, and then there are global limitations. Yeah.
Thank you so much, ma'am, for such nice informative session that you delivered. Now I request all the participants that you need to join back again at 1:30 for the post-lunch session of Professor Sharma, and a topic of that session would be storage, transportation, and safety aspects of hydrogen as an energy carrier. So now, thank you so much everyone for joining. I declare end of this session here.